Hello, everybody. My name is Kevin Kawchak. I'm the founder CEO of Chemical Q Device, here for discussion 92. This is July 20th, 2023, for quantum machine learning platforms for healthcare applications. So you can glean a lot from these release notes. And the way I'm going to run this one is I'll post in the chat, and then we can all follow along. So for instance, in this specific one, there's also this is the introduction. In previous ones or subsequent ones, there'll be links to the actual, so Penny Lane, Qiskit, there's Google Cirq, and then there's AWS Briquette. So just a little bit as far as release notes go. So they can range anywhere from the notes that you get on your phone. They're just very general. They just say we have bug fixes and improvements, and they can get very casual or even humorous at times. Now, the ones for quantum computing are a lot more specific because it's still getting, a lot of these details are getting worked out. And you'll see, so most of these use, it's called the semantic notation. So semantic notation is major dot change minor dot if there's a change in a patch or a bug. So for instance, a 1.0.0 would be a major change of 1 with no minor change and no patch. So the major changes are typically significant changes, and they may present compatibility issues. So for instance, if you've been using a specific notebook and all of a sudden you hear of an announcement, heads up, it could change or break your code basically if you don't make the necessary modifications for it. So a minor change is basically, it could it's basically usually not an issue with compatibility with minor, and then patches are more like bug fixes. The reference for this is OpenAI. So why even bother, right? So many people don't even look at release notes, I don't think. They just go ahead and program, and then as soon as something breaks, they think it's just a random occurrence. But in fact, you can plan better performing future experiments if you kind of know what's going on. So I'll get to an IBM Qiskit, and it says for that specific one that in this future release that when you do a pip install, that your typical simulator called AER, A-E-R package is not going to be installed with the regular with other things in Qiskit. And then also fixing models that are incompatible with the current release. So this is everybody's nightmare. You open up your computer, everything auto updated, your model doesn't work, you didn't lock things down as far as version control, those types of things. And then the third thing you can see in the chat there is basically learning techniques for new quantum algorithm developments. And I'll look through these and they'll be like, we're updating this, especially in Qiskit, super technical. Now, the first part is Cirq. So if you're just joining, it's in the chat. So with Google Cirq, let's see here. This one should. Sometimes I have to go a little bit at a time. Okay, so we're in the chat here. So you see part 1 equals Google Cirq. Here's the link to their releases. Now, you might know Google came with quantum supremacy, and after that came Google Cirq. So they're already on their first major release. So it's Cirq version 1.2.0. So .2 is the minor release, and this is not considered just a bug fix. So Cirq protocols and simulators now support gates that allocate new qubits as part of their decomposition. So anybody that programs it in QML, these types of things, this sounds like it's a huge thing, right? Now supports gates that allocate new qubits. So it's sounding like more qubits, those types of things. And if you don't understand it, you can ask around these types of things, and we'll have time for Q&A at the end of each part. So this is part 1. So it says Cirq-FT, the second bullet point here, is a new subpackage for rapid prototyping and resource estimation of fault-tolerant algorithms. This is another big trend that you'll find in release notes, is everything wants to be towards fault tolerance in hardware. Now, the majority of, like, say, bigger experiments or, lots of data or medical images are still run on quantum simulators, CPU or GPU based. But that's the whole push, is basically for a lot of this to work on emerging hardware. And you'll see this is all fitting in. It's a classical world out there. It's not quantum yet. It's not even close to being hybrid classical quantum. So you're still dealing with it's in a Python framework, dropping support for Python 3.7 and 3.8 and adding support for Python 3.11. So 3.11, I believe, came out later last year in 2022. And you'll see I included this one, and this is, you can click on these links too to follow along. And I picked one, and it says fix failing CI after Pandas 2.0. So Pandas 2.0 was recently released, update by this author. And if you click on this hash 6051, it's a link to GitHub, and you'll see the author's notes. So again, all of this is in the chat, so that I'm putting in here. And it says for the author's notes, CI is failing on master because PyTest on Windows are failing. Upon some digging, it looks like a new release of Pandas 2.0 today broke us. So meaning you'll start to get into the lingo, right? Especially for some of the other release updates that aren't quite as technical. But, if you're any at all interested in being a developer in QML, you're going to have to be proficient in release notes, change logs. Sometimes they call these different things. And then, so for this other one, so we had CI, and then let's see, and then these last two for Cirq. So you'll see in the chat there, Cirq, and then a version 1.1.0 is tracking and improvement performance of key workflows like circuit construction, parameter resolution. And just like if you're reading papers all day for quantum algorithms, that everything is not cement yet, like things are working pretty well if you work in Penny Lane or Qiskit. And I've worked some in Cirq and a little bit in AWS Briquette. And it says the release also adds a new transformers. So transformers is huge in artificial intelligence. So it's good to see this stuff, right? Transformers, maybe better performance or better speed associated with that as well. And they quote this archive paper at the end. So this 1902.08091 is from 2019. So, you kind of dig through papers and they're trying to make things work better. And you can kind of see this kind of meshing. And then this last one, Cirq version 1.0.0 is officially left alpha and is now version 1.0. With this release comes new policies on API stability, and it goes on. So, out of the ones that I researched, this is the only one that I've seen a 1.0. So I think that might be a terminology, is basically you're leaving pre-alpha to alpha, and then you can go on to beta with a lot of those things. So I'm going to open this up. So that was the end of part one. There's 4 parts. It's according to the slide that I put up in LinkedIn and other sites too. And this is Google Cirq. Are there any questions regarding these with this first part?
Hi, this is my first time attending. I'm not really sure what's supposed to be happening. Sorry if there's like a presentation that I'm missing, but it just seemed like a whole, kind of a lot of words, but I didn't really understand what.
Okay, so yeah, if you joined a little late, it's basically, so these are release notes. So every quantum machine learning platform has their own set of release notes. And then, so this is basically getting QML to the point where, it's more reliable, it can do more things, more qubits, larger circuits, those types of things. So it's the process of all of these, and I'm putting it in the chat, and the links are in there as well. So you look at the release notes, and then you're like, okay, I'm planning these experiments. I see that this function is going to be available, or even sometimes things are deprecated that you'll need to adjust your code to. So yeah, that's the basis of release notes, is it's the message to the public that this is what is being changed. And a lot of times they'll say why, and then they'll say this is for the future too. So for instance, like with Qiskit, I'll be getting to, it'll say, heads up, because we'll be changing this in the code. So it's something that developers kind of rely on it and trust people, with release notes.
Oh, okay, yeah.
Yeah.
So will you be doing any kind of like lectures or something? Essentially, my background is that I'm trying to make use AWS bracket, and you can make it compatible with some kind of neural networks, and it would be good to just like see what's being done in this space. And I thought, and it is for medical purposes, so I thought this forum would be related to something like that. Is that correct? Do you
Correct. Yeah.
think?
So AWS Braket, for instance, they just recently nixed support for Xanadu's photonic quantum computer. So your code that's based on this photonic, platform will no longer work with AWS Braket. So they've recently added a second IonQ quantum computer. And I don't think you can do quantum annealing on there, but these are all from these things called release notes. So it's like the guide. Some might say it's the hard way, but it's kind of the only way. And then perhaps sometimes down the road, you can meet some of these people that create the release notes, and then, have relationships, or, appropriate ones that say, oh, okay, if you're trying to do this in medical, that you have to be aware of these changes. So it's the result of the technical changes going on behind the scenes. So a lot of this, many people don't ever see. It's just all of a sudden you run your code, and if there's an error, say for instance, there was a drop in or an addition in a simulator, and now these other ones are deprecated, or this other one is deprecated, you have to be aware of what's going on behind the scene. So
Okay. Yeah, that sounds good. So the nature of the format of these sessions is going through the release notes and seeing like what's most up to date and things like that.
yeah, it just depends, so other ones I've done gates and circuits. So for instance, this is how I did demos on quantum algorithms. So in IBM Qiskit, and this is how you do that. I've done other ones where it's more like the lab work behind it, or like inside notebooks. So yeah, this is one of the steps, that's taking to get to that point of being a proficient developer in quantum machine learning. So, understanding all this previous background, that, it's one of those things you can't skip. It's just like if you were to help people on forums and QML, and your next step might be to, on your platform that you're using, you want to stay up to date with the platform. So the second one, so the IBM Qiskit, and was there any other questions regarding part one? So part one is Google Cirq. Any general questions? So as I mentioned before, a lot of this is going into a classical world that we live in. So it's hybrid quantum classical computing is doing QML platforms in either of these four. So part two is IBM Qiskit, and I put in the link here, so you can click on the link, and these are IBM Qiskit's release notes. So the most recent things that happen in IBM Qiskit is they dropped support for a platform called Aquas, like the water, and they dropped support for a platform called Ignis. So if you find these old notebooks, like from 2020 or 2021 even, I couldn't run them, right? And if I would have, looked at the release notes, I could easily see off this chart that it puts up front that it's no longer supported. And I had to make changes to the notebook with the simulators I was using and other things as well. So basically here, so the most recent Qiskit version is this 0.43.2, and they're saying the next minor version of Qiskit Air will not be included in any release of the Qiskit package. So this means Air is for simulators, quantum simulators, which most people are using, and that's just, if you're not aware of that, your notebook would crash and you think it's a random occurrence. So then improved performance. So again, these are for like, you have your notebook and you're running it in Google Colab, or you're running it, locally on a Jupyter Lab notebook or IBM Qiskit notebook, and you're trying to gain better insight into it. Also with this version, improved performance when the same circuits and multiple parameters are passed to estimator with approximation equals true. Upcoming Qiskit version 0.45, here it is. The pip install Qiskit will no longer install Qiskit Air or the obsolete IBM Q provider. So these were popular tools that people are using. And it says, heads up, you have to change the way that you run your notebooks. So if you're a developer, especially, these are the types of things that you have to be aware of. Also with the next version, so this is version 0.43.1, some updated plot gate maps, error maps, circuit layouts. And what's interesting about this one is it says 433 qubit heavy hex coupling. That's the next processor. That's the next QPU or the next quantum computer, the Osprey. Okay, so it's trying to make room or fix things as IBM and other platforms will be releasing additional hardware. And then also fixing a bug. This is called block collapser, and you can look up what block collapser is. And also another one, these are the things to be aware of. An RZX gate, you might be running, but it says there's an error with it. And if you don't look at the notes, you would assume that it's some random occurrence and that you might not further pursue other parts of the quantum algorithm. So these things are definitely essential. And then this last one for Qiskit, I put in the chat here. So major feature release. So it's a 0.43, which means it's technically minor, but they say major feature release. Includes numerous new features and bug fixes. And you'll see this, it's heavily dependent. I think most of it's Python. So your notebooks are Python based. It has other classical components, and then this as well. So there are associated migration guides, for this process as well. So that was Qiskit. So that's part 2. Were there any questions regarding this? And again, this is developer work. This is very specific stuff that if you're running code in quantum and it's not, seeming to work, or you're missing out on benefits, is because, it could be you're not reading the release notes. Okay, so there was a question here. So Dimitrar, would such changes account for errors in running code on learn.qiskit, which tries to schedule computations on available resources? Are changes happening often? So, always refer back to the documentation. I'm just going over a couple of different releases. So as far as I know, a lot of this is fair game, right? Like everything is updatable. And if it's updatable, it's probably near impossible to keep things backwards compatible 100%, right? So in any emerging technology that's both hardware and software based, is that you have this interplay where things are going to change on hardware, or say like you want additional capability, but it may change backwards compatibility. So it's one of the things that, likely developers and other, parts of these platforms, they sit down and say, okay, this should change, this will break this, meaning the code won't work, or this will make it much better for the majority of the people, those types of things. So, it's just like with anything, it's, something you have to keep up. And were there any other questions regarding part 2? So that was IBM Qiskit. And then, so this is part 3. So part 3 is Xanadu Penny Lane. Now, I try to split my time. I try to stay agnostic to platforms. Most of the good models I found, Penny Lane has a lot of them, right? So it's pennylane.ai. And it's anywhere from just like, if you're doing optimizations to like, full quantum transfer learning models, those types of things. And the big news with that is they just announced multi-GPU support. And it's called cuQuantum, and basically, that opens up a lot of things, right? Because simulators are slower anyway, but if you can get the performance from your algorithm that you need and then try to catch up with the speed so it's just not so slow, then this is a huge thing. Now, Penny Lane has 2 things, and I put 2 links in the chat. So the first one is basically their blog, and it's more images and kind of like attractive. And the second one is more, it's their release notes, right? So the first link in there is just for, I think just for that specific link. So you see 31.0, they say seamlessly create and combine fermionic operators. So I think this is for quantum chemistry. Here you go, Penny Lane Lightning GPU now has multi-GPU support. And this is huge. Like, there's such demand for GPU in the classical world. And now you're gonna, likely get help with the simulators, so they're not so slow. A new set of quantum circuit resource estimation functionalities, community contributions from Unitary Hack, qubit base, and I've done some stuff with qubits. I've gone up to 10 dimensions and qubits. So it goes qubit, qubit, so on and so forth. So the other stuff, so it's 31, and then they have in other recent releases, and these are the types of things like you just want to be thinking. It goes back to like, how can I get better performance for my algorithms, or how can I keep it from crashing and know what's going on before things they change something in one of these releases. A huge thing coming up, most of the programming being done, as far as I know, is called state vector. Now, state vector are pure states, they're not mixed states. And the hardware pulse programming allows you to have a fine tuning of qubits to a greater degree. It's typically better performance, but it's just harder to do, especially with certain types of hardware. So this one says hardware pulse programming added. So pulse programming is fine-tuning the quantum states through electromagnetic pulses, which is hardware. And as far as I know, it came out on simulators. So they also mentioned things like this quantum singular value transformation. It's associated with SVD of a given matrix. So this is where you're looking through papers, you're trying to find advantage. Which platforms just add a qubit support, which platforms just have, this pulse programming, these types of things. And you also have, updated Q node returns. Things are getting better. Some of the simulators don't work on some of my models, like say, for instance, like a default.qubit. And then if you're trying to do lightning.qubit, it just doesn't, they have charts for this too. It's not quite as compatible with a type of code that you're doing. And then you have version 0.29 supporting for creating pulse-based circuits. So this is, you work a lot with gate-based, and then a lot of people will experiment with pulse-based programming, try to get that extra edge if you understand what you're doing. And then also second dash here for 0.29, special unitary, your own unitary. So this is your own quantum circuit kind of thing. The Hadamard test. Now there's other types of tests too. There's swap tests. There's a swap Hadamard called a swapamard test. And you'll start to see these like, especially as things evolve here. So that was Penny Lane. So that was part 3. Were there any questions regarding this? So in general is fine too. And then if you have any questions regarding Penny Lane release notes, feel free to come on, or you can ask questions too. And, kind of curious as far as everybody's journey too, like, have you been programming, like myself, like most this week, or you're, just getting started is fine. So these are things to put in your tool belt, when you get to that stage of, release notes, or, put them into practice right now. Now, earlier, and any other questions regarding that? So this is part 3. Earlier, there was a question regarding AWS Bucket. So I put into the chat here. So this is part 4. And the first one is a very general overview of what's happened. Like I said, there was a drop for, there's no more photonic support. So you have code that runs, on photonics, quantum photonics. You can't no longer do that. They've added a second IonQ quantum computer. I don't think you can do D-wave annealing anymore. But I think that the big drive is towards this ion trap quantum computer, especially in the near term, for the best support. So theirs is split up into a PDF. So it's called document history for this is AWS Bucket. So this is the update regarding the Xanadu devices, these photonic devices. And then 5.16.23, you see it added support for IonQ area. So they have two different ones. I think one's in the teens and one's in the 20s as far as quantum bits or qubits. And they also have the 117. So the added support for Rigetti. This is a gate-based superconducting qubit M3 device. And their changelog is a little bit, I mean, it's not super detailed, but you could see this pulse delay and barrier, that there's a push for this pulse programming. Some developers, believe that there may be a shift away from gate-based, quantum computing, which is, well, you could probably still do state vector, but gate-based, meaning that like Hadamard gate or whatever, there's limitations to it. So that's where, pulse programming could really start to get big. So this version 1.43.0 adds support for Python 3.11. So this is the most recent version of Python from later last year. And then you also have pulse plotting in version 1.42.2, which is a bug fixed, because you can see the .2 with it. And they go on and on and on. And I wanted to give you a sample of all of this. And again, a summary of the importance of checking release notes, right? Like this is the way officially that companies communicate with developers. You could also be talking to people, you have relationships as well. But I think especially for quantum computing, you see that there's a fair amount of, work and, it needs to be communicated to the people that are developing code. So planning better, performing future experiments. We saw that with Qiskit, there's dropping support with this, version, I think it's 0.45. And then fixing models, right? All of a sudden your model doesn't run. And this, they try to have this not happen, but it happens. It happened to me. I opened up a bunch of IBM Qiskit notebooks from several years ago, and then I had to figure out what was going on. And now it makes sense, but I was searching the web and, this Ingus and this Aqua, these two things, or these two like platforms they have within Qiskit, they're deprecated. So the models wouldn't work. And then number 3, again, learning techniques for new quantum algorithm developments. So in one of these, it actually mentioned a specific gate, that they're fixing and making better. And you learn things, from other things that say, you're looking for specific things, but a lot of times you're learning, many things that you weren't intending to, but you need later, right? So you're kind of like accumulating all of this knowledge. Any questions? So this was part 4, so AWS Briquette. And any questions regarding this or any of the other parts? So there's, Xanadu Penny Lane, there's IBM Qiskit, and, Google Cirq. So are you using a certain platform? Do you want to get into another platform? And feel free, you could also put in the chat as well. And I hope that helped, because this helped me a lot to kind of see what was going on between different quantum machine learning platforms, especially for medical data. So, it's the type of thing that, it's not just one thing. Like if you want to be good at quantum machine learning programming, you have to, find out what's going on in release notes, go to different forums, watch lectures, read a lot of papers, those types of things. But quantum machine learning is predicted to be, or is the primary use for quantum computing. So it's taking that, machine learning background that we have in classical, adding quantum circuits to it, and there's no reason why it couldn't just take off, if there's big news in hardware or software too. Okay, so there was a question, which platform would you say is better for beginners? So there's an IBM summer camp going on right now. It was too late to register for it. I get caught up with papers and other things. I would definitely start with IBM. So you can start, the funnest thing is to do graphic or composer. So you can slide in different gates. And I'll put in a little link here. It helped me a lot. And it's basically you click one button and it sends the circuit or the algorithm to the composer, and you click again, and all of a sudden you can run on a real quantum computer or even a simulator too. So it's under entanglement. But I would say a lot of people learn in bits and pieces like myself. You can take more formal courses and certificates if that's your preference. If you audit, you typically don't have to pay. And then if you want a certificate, then you do. So for those getting into it, and this is for Dimitri, so you can click on that. And then if you scroll down, so it says open an IBM Quantum Composer, it sends the circuit straight to where it needs to be. Like you didn't have to do anything as long as you have a IBM Quantum account, a token ID is what they call it. And then just click run the experiment. And it's like, it's the quickest thing in the world. And you can make modifications to it. So if you have a hunch, add a gate, double gates, triple gates, these types of things you're reading literature, is you can make those modifications to it. Anything else, Dimitri, as far as getting into it? I would definitely do the forums. A lot of this stuff is set up, the elementary stuff, or like just getting into it where, maybe the release notes wouldn't be the first thing that you did, but, more for advanced users. And then besides that, definitely research the gates. So it's Hadamard. There's many different single gates. There's rotational gates, RX, RY, Z. There's single gates on their own, X, Y, Z. There's Hadamard gate, which is really unique. So in Hadamard, you basically split. You have a linear distribution between binary. So it's linear distribution between 0 and 1. And from there, you can rotate that quantum state. And then at the end of it, you're measuring, and the quantum state collapses, and it's back into a binary output for classical use. So that's what happens a lot of times with these, is that you'll have something before that was classical, you'll do quantum transformations to it, and then your output will be a 0 or a 1 for that specific qubit. Okay, so if you're coming from, this is another question too. So if you're coming from classical machine learning, how would you compare it to quantum ML? So quantum ML is basically just, in these days, is because of limitations and simulator speed and quantum hardware, is basically adding a smaller quantum algorithm to hope to change the data set in some way that it's advantageous in the middle of a bunch of quantum code. So these are called parameterized quantum circuits. So typically you have to embed the data. So you'll have classical data, so binary 0s and 1s coming in, and that classical data has to turn into quantum data for the quantum circuit or algorithm, and that's through an embedding layer, so quantum embedding. And then you can do stuff in quantum, and you're limited by how long it would take, on a simulator, or if it's too noisy for a quantum computer. And that information is measured, okay? So that measurement produces binary code again, so 0s and 1s, and then you can do stuff, whatever you want in classical again. So it's basically interrupting the flow. And say, for instance, I want to, and I've been reading these papers, I want to more focus on, the quantum embedding, right? So it's taking data sets and distributing the data over a quantum bit in a way that classical can't do. So this is like the quantum physics or quantum mechanics behind it. So you could do that. So superpositioning of the qubit, some rotational gates or gate, and then your variational part, which is more like that part, plus entanglement. And then your variational part is more like the deep learning network analogous to the classical world. So you train the parameters, these theta angles of rotational gates typically. And then after every epoch, or say every part of the batch, it's updating those parameters in an analogous way that you would have weights and biases with deep learning. To do it that way, right? So there's a million ways you could do this, more than that. So that's what researchers focus on is today, given the limitations that I've been mentioning in simulators and real hardware, is it's more on simple circuits that are doing things in a quantum physics way that you can't do classically, but it's just like, oh, that was easy. But we just distributed our data like this. And these days, it's harder to get a quantum speed up because the quantum computers are too noisy, and the qubits aren't high enough. So that's what it looks like, is you can get performance benefits like accuracy or loss, or higher accuracy, lower loss, taking advantage of just you have a quantum bit and the physics of it in a simulator. So yes, yeah, you're trying to take advantage of the superpositioning, entanglement, interference, the physics of the quantum bit. This is different than classical to process data. Okay, so there's another question here. If you're okay, so that one. Any other questions? So we went over these 4 parts and the release note. So if it's not relevant now, just put it in your pocket. And then it's a type of thing that it's important, you have to stay up to date with developer news, right? So I'd say that you'll hear people, oh, they just code by themselves. They're awesome. I think more often you find people that are connected to the outside quantum world, forums and release notes and, meetups and Zooms and these types of things where you discuss everything that's going on in quantum. I appreciate the question. So, and, depending on people's backgrounds. So one person said, coming from classical machine learning, is that in many of these things, so if you have a support vector machine, there's a quantum support vector machine. And, if you have a certain type of neural network, now there's a quantum neural network. It's different though, right? So instead of having this nodes, like a convolutional neural network where you go out to 4, come back to 2, hidden layers, these types of things. Instead of training those weights and biases, now you're training these rotational values on qubits. Like anything that can be trained is, we're doing theta, we're doing angle rotations now, making it better every pass, that kind of stuff. But in the future, more things to train on. So there's a lot to look forward, especially, if you're running simulators, they're noise free, they're slower, they're limited in qubits. But on the physics end, if you really understand something, you can have, in my opinion, a relatively simple circuit or algorithm that's doing something in a very advantageous way in using quantum physics and qubits, as opposed to classical, that you're just restricted to zeros and ones and not like all of this information that we have in available in quantum circuits. Any other questions regarding the quantum side of it? So definitely, I was in this kind of government call. It's QEDC, or Quantum Economic Development, and they have a stack. So your stack would be like application algorithms, and then framework, and then even more specific stuff at the bottom. So, you have to think of all of this. Like, do you just want a killer quantum algorithm, or do you want the application, or do you want the whole framework in your specific industry? And it's literature is very encouraging, and at that same time, I would not consider that it's fully meshed, like as far as, and it never will be for classical research either. But as far as all of the ideas and concepts coming together, a consensus. So it's a lot of trial and error, because you'll read a paper and it'll say this works here, and I'll go ahead and try it, and then I'll read another paper and they'll say like, oh, this works. And then, there's still an experimental component of it all, if that makes sense. So as far as other beginner resources, there's models. Actually, I have some of these. So the best models are your IBM Qiskits, Penny Lane or Xanadu Penny Lanes. There's really cool. I'll put some Google Circs in, because I think I was running these. So if you have a Colab account, they're simple. So you just go run in Colab. So here's 2. So if you look in the chat, now this first one is based on a simulator that was in comparison to the quantum computer from October 19 publication in Nature. And it's a 90 core Xeon simulator. So depending on how much data you have, they say up to 40 qubits, it's free. So for that one, so I've been trying to use, so it's called Google Cirq QSIM, QSIM. So that's probably, if not the top quantum simulator as far as non-GPU, open access, free, that kind of stuff. So I would definitely check out that one. Now, the second one they did with QSIM was the biggest circuit I've ever run, using quantum simulators or hardware, 32 qubits, a depth of 14. So that means going up and down, 1 qubit, 2 qubit to 32, and the depth of the quantum gates, it's typically per single wire qubits. So it's 1 all the way up to 14. And they have entanglement, and it's very interesting. I don't think the problem was that hard, but these two that I put in there with QSIM, that seems to be a good, like if you have a head start with Cirq or other Google services to start using QSIM. The other one I think is Cirq.simulator, and they said the QSIM is a lot more like 90 core Xeon. It's classical processor, it's not GPUs, but you don't have to pay for it. Like GPUs figure rental time, you're paying for it. So I found those two, so you could try those out. Yeah, there's a qubit one. So qubit is a multi-dimensional qubit, and then you design your own X gate, and then you're effectively running it. Similar to the way that you run like a Qtrip or a Qcourt, those types of things. So any other questions? So, if it's anything beginners, it's fine. I mean, it helps everybody. And, if you're coming from a certain background, like, classical machine learning, those types of things, is you have an advantage because the hybrid models, even though they have quantum code, everything is classical beside that quantum code. And you're converting classical code into quantum for that time being, and it goes back into classical. So if you're very good with optimizing an overall model, or say loss functions, all these types of things, and ReLU activation functions, a lot of these concepts are still relevant to hybrid programming, right? Like think of it like this, like the quantum circuit is doing something in that time to help, process the data in a different way, that's hopefully advantageous, but the bulk of it is still going to remain classical code. So yeah, it's definitely the type of thing that, you want to know both classical and quantum. If you just have a quantum algorithm, you might get lucky. People around you know enough how to use it in classical code. And then I'll put a couple in the site here. So these are some IBMs. So this, if you watch these, and I think they're both YouTubes, watch those two. These are two YouTube videos. Now the first one gets into discrete log functions, which is basically a way to get quantum advantage. The second one is how to apply it. Now, in these types of things with embeddings, so probably the most important port, you don't always need variational layer, but you always need embedding and measurement, the two ends. And with these, it gets in, especially the second one, the practice, quantum kernels and practice. You figure out your math, and then you design a circuit around it. And then it should work if you did your calculations right to distribute the data. Say if you do binary classifications instead of two clusters on either ends, now the data is in two different points. This is ideal case scenario. So one class of your data is on one side of the quantum bit, and the other one is on the other. And then you have linear separation between the two. So that had to be done in a certain way, and she walks you through that. It's a very helpful. But that's the theory, is if you understand the math behind it, is that you can go math instead of just trying everything on your own, quantum circuits and randomly doing things, which people have done and I have done too, is you start with the math and then you say, okay, this will do this. It'll separate in a certain way. You're taking advantage of the physics of the quantum bits in a way that you can't do classically. So there's another gentleman, Seth Lloyd, that has done similar things to this and has mapped data to different parts of the quantum bit. So either coming off deep learning, like 512 elements kind of thing, or doing it with a simple data set. And I have that paper too. And I'd be interested in, as far as what people are getting into or want to get into, if it's medical, finance, these types of things. And, it's a type of thing that there's billions of dollars behind quantum computing. And IBM installed a quantum computer at Cleveland Clinic. NYU Langone Hospital is working with Fermilab with MRI analysis with quantum sensors and quantum computing. Sandbox AQ with Mount Sinai Hospital with quantum and data protection. So it's with the big health systems, it's something that is definitely underway, right? It's not taking a complete risk to get into QML and healthcare by any means. So awesome. Any other questions? So went over the release notes, and then this is definitely like, you find these awesome papers and then you try it, and then it's definitely iterative approach. But get Google Colab or have a good setup, that you're running locally, Jupyter Lab notebooks. Definitely get a Qiskit account. So somebody asked, what's a good thing for beginners with all of this? Is Qiskit, you get free storage and notebooks and all this type of stuff in the Qiskit, IBM cloud. They have all these tutorials. People are going through summer school right now, and it's a good place to start. Like the graphical composer, sliding gates into places and, doing embedding layers and variational layers is, it's cool, right? It's different than classical for sure. Anybody that we haven't heard from? So Abhinav or Gervais?
Hello?
Yeah, go ahead.
Yeah, I have no question.
Okay, Abhinav?
Hello, yeah. So I didn't realize what the context of this, the focus of this group would be today. But yeah, I have a strong background in classical machine learning, so I'm still new, very new. I'm not very familiar with quantum yet. So
yeah, and then I would get familiar. It's called the block sphere, BLOCH, and it's basically it's the representation of a quantum bit. So when you have a quantum bit and it's coming in, you have an embedding layer, you could do different things to it. So if you go across a wire, so wire is a representation of a quantum bit, oftentimes the first operation you'll do is called a Hadamard gate. So that information coming in, if it was a 0 or 1, it'll take that classical information and it'll form a superpositioning of 0 and 1, okay? So then the advantage usually comes in with these other types of quantum gates that take that superpositioning, this linear distribution of 0 and 1, and then it does a bit flip or a phase flip or rotates it. And then you can also do entanglement. So entanglement is tricky these days because a lot of times it doesn't get you it's not the most important effect. But say, for instance, when people get into quantum computing, they'll hear of this. It's called, the mathematical expression is 2 to the n. So if you have n number of qubits, you have that much of information. So 2 times 2 is 4. So 2 to the 2 is 4. 2 to the 3 is 8. And once you get up in qubits, your mathematical probabilities for the amount of information, like sheer amount of information, goes way up for quantum, but the problem is the noise in the quantum computers and then the simulators takes so much classical RAM to try to get to that point. So the two camps are this, is basically you're trying to either take advantage of the physics of a quantum bit, or you're trying to get exponential speed ups and more information and these types of things. It's trickier to do on quantum hardware. So many of you have probably heard of Shor's algorithm, RSA encryption. If you have a quantum computer that has, so many thousands or millions of quantum bits, that in theory that you can break today's, 4,000-bit encryption, okay? So the same thing with medical is that if you want to do medical images, you can either, try to separate data better over a quantum bit, or you can try to go for exponential speed ups if you have the quantum computer. So that's where the struggle is right now. And I would say that there's advantages in quantum, especially with simulators, in data processing, right? The way that the data goes over quantum. So to me, it's very simple. You just have some part of the quantum, some part of the deep learning model that you want to convert that into quantum, do stuff with quantum, and then convert it back into classical. So for instance, if you have a classification, I've done this a number of times, like 44 classes, where the information is coming off of a convolutional neural network, say 512 elements, something like that. And you'll go into like something like 20 quantum bits, and it does quantum processing. And at the end of it, it goes back into binary, so zeros and ones. And then it's the final classification is based on this hybrid network. So it's really not as complicated because there's a lot of information as far as quantum computing. But for hybrid models, it's basically classical to quantum to classical. And then many models, I do a quantum transfer learning model, has most of this worked out, and I was able to understand how to improve classes from 2 to 4 to 10 to 44. So I would definitely start with models too, like understand gates and circuits and the differences. And, if you were to, the US government spends $800 million on quantum information sciences. This is the past 3 years. And you'll see development not only in NIST and NSF and DOE, to further advance all this, but especially in public and private sector. So I would definitely recommend, getting into it. It makes sense to know what's going on so you could eventually use it for your application. Did you have any other questions, Abhinav?
Yeah, so if I understood correctly, with the quantum computing, it basically allows you to do high throughput parallel computing or run parallel networks if you want to get kind of like a large amount of data, correct?
Well, there's a thing called quantum parallelism, but it's not the same thing as massively parallel classical, HPC computing. So it's the parallel world of quantum. So today you're basically limited with quantum simulators, which don't have quantum noise because they're not on a quantum computer, but are not native. So it's not natively quantum like a quantum computer is. So they're slower. So in that case, more people are looking for better accuracy or lower loss, as opposed to something that would be slower. Now, I'll give you a good, besides doing quantum models, there's many cases. I was on a call, this government call this morning, and Quantum Algorithm Zoo is a good website. The gentleman works at Microsoft, and he's been working on these. It's basically all from literature, right? So you still have to look through literature. I'll give you an example. So here's a common one. So you have a classical algorithm, a quantum algorithm. They're both known to have the same quantum speed up. If you run the classical algorithm natively on a regular CPU, it will always be faster because the quantum algorithm, although it has the same speed up today, if it's run on the simulator, will be slower. Another example is if you have a classical algorithm that's inefficient and you have a quantum algorithm that is efficient, and you do that same thing, one on the regular CPU, one on a quantum simulator, it's not without doubt, or it's not without reason that you could still get a quantum speed up, because that classical algorithm can't quite do that task quite as well. So it's an in-depth thing. It's definitely complex as far as like, it's not always apples to apples. And there's 3 approaches, and these are from those IBM videos. So you can have a classical algorithm that's inefficient, and you switch over to a quantum algorithm analogous to the classical algorithm. You update parameters, you optimize it, and that's one approach. So one of 3. The second approach is to have a quantum algorithm that's known to be very good. So it's efficient at what it does. It has good mathematical advantage. And then you further optimize this, with parameters, those types of things, add entanglement, those types of things. Now, the third thing is what I was talking earlier. You have a data set, and your data set dictates what your quantum algorithm should look like. So based on if you have binary data, certain, looks a certain way, you have mathematical proof, basically, and you turn that mathematical equation into a quantum algorithm. So yeah, it just depends, right? But there's this D-log function that many people have recognized as if one of these ways to speed up the quantum has the advantage in this specific case. It is in that IBM, the lecture 6.2. So a lot of us, sifting through lecture, because it's not like, it's not like classical where it's just like, yeah, we have a pretty good idea with deep learning, but you still have to update, whatever. If you want to use atom optimizer and specific loss function, it's not as well known, right? But you could still run into things, I would say, in literature where it would help. Is there a question, Gervais?
I have no question.
Anybody else that we haven't heard from in a while? So we have Edwin, and we also have Michael. But as far as references go, I mean, there's usually, if you have questions in quantum computing, you can find the answers in literature. It's just you have to search a little bit. So for instance, like if you have a cookie cutter model from Penny Lane or even IBM, even though I've kind of like maxed out, I got 100% on certain IBM Qiskit model, is that there's always more in literature, it seems like, which is good because you can find your answers. So this is, I'll put it in the chat. So the quantum transfer learning model, I've been able to take pretty far. So like I said, increasing classes, increasing data set size. So for those that don't know, transfer learning takes advantage of a pre-trained network, and then you use that same network like a ResNet 18 in this case. And then also in this case, you add a quantum algorithm. And then I compared that to 2 other classical models. And so I had 2 comparisons to 2 other different type of transfer learning models in this case. So, it was good because I got number of classes up. I used 20 qubits. There's about 8 other papers that do medical image analysis like this. And the most I've seen is 4 qubits and 4 classes at the expense of accuracy. So more classes, typically lower in accuracy. But I did it, I was able to do it in using quantum computing, smaller quantum circuits. So awesome. So any other last questions? Saw some people kind of jump in at the end here, and then Edwin, if you have anything. And if you want to, see what's going on, there's 2 things. There's Womanium is going on right now. And then this one is, I find it best through YouTube. So they have all types of lectures. Now I'm on the super technical end, and I've only found one that was like that. as far as like, I knew some of it. So here's the link to Romanium. And then the second one is Qiskit Summer School. And in the past, these two videos I added from IBM are from a previous, the 2021 summer school. Very helpful, super technical. If you've been running models for a while, it helps a lot. And then this one, although registration is closed, it gives you an idea of how big of the, relative to what quantum was, say 3 or 4 years ago, how it's gotten bigger, I would say. So, it's got the schedule and the kickoff and all that stuff. So awesome. Any other questions? Anybody that we haven't heard from yet? Appreciate, because definitely have people that are kind of progressing through that, the Qiskit stuff and Penny Lane, but just don't give up, right? When I go on different panels, they're scared of quantum, because it's like they didn't go to school for quantum. I didn't go for school for quantum. And I just said, I'm going to learn from this, from lectures and papers and, running my own models or running models that are based on quantum. So I wouldn't say you don't have to have a PhD in quantum to do it, right? So I've come across people that do, but I've come across people that didn't have technical experience as a bachelor's that are writing, books and Medium articles on quantum computing. So don't be intimidated, I would say, and do some of this Qiskit stuff, like running Cirq, like just send the circuit straight to your composer and run it. Like you just ran a quantum circuit on a real quantum computer or if a quantum simulator. So don't be intimidated by quantum. There's some good books out there. Quantum Computing for Babies is like a little kid's book, but Bob Kuka, he's from Quantinium. He puts out a lot of good stuff. That's see if I have. He's one of my experts that I follow. So here's two experts, Bob and Aiva. So 2 different companies. So Bob's stuff is pretty good. The ZX calculus is basically spiders. So looking at quantum circuits as spiders and, it's just it's a different approach. It wasn't the way I was taught, with quantum. And then the book is called Kindergarten Quantum Mechanics is the B one. So then that's an archive. So that's open source, lots of pictures. I'd be happy to hear. I mean, I had somebody just say to me they watched all my videos, which I don't know if that's possible, but that there's growth in this basically. So the Kindergarten Quantum Mechanics, and then the Aiva one, there's a YouTube, there's a molecular machines, so for this is quantum chemistry kind of stuff. So awesome. So anybody else, feel free to put in the chat, or you can unmute or unmic yourself, or you can come on.
Yeah, thank
I have
you,
a
Mike.
question.
Yeah,
I
go
have a
ahead.
question. Is it possible like to work on building a quantum computer project? I was thinking about try to work on quantum computing project, and I'm kind of thinking how the cost could be, and is it still just for high industry to build the quantum computer, or can someone try on its own?
Yeah, I personally believe the best way is to run. So take that IBM Qiskit, that entanglement link. So you could download the chat. So it's that triple dot, and then you just save chat. And definitely start with that, because it's like you ran a quantum circuit on a real quantum computer. More than likely, you're going to be working on quantum simulators. Number one, because of cost. The IBM 7 qubits or whatever, sometimes there's a wait for them, but they're free. So I've run on Nairobi typically, but yeah, run the quantum circuits on Qiskit in Composer with that entanglement link, and then just open up Colab or whatever works. I know Colab works, and just run that quantum transfer learning one once. You have to have the right data set. That's the only thing, like your data dir. So is, you know, that has to be correct for that one to work. But just run and then take some, I just learn all over the place, you know, take quantum tutorials from, you know, internet. I would take a IBM Qiskit, like the single qubit gates, and I presented on it. It's very effective to learn and teach and to develop, right? So learn from IBM, whatever, from Penny Lane, whatever, teach on it, right? You'll learn better and you'll find out what you don't know. And then develop, right? So run models, but learn, teach, develop. I think that's an effective approach.
Thank you.
I just have one last question.
Yeah.
So it seems like there are a lot of useful resources in the chat. I was wondering, will this recording be made available with the access to the contents from the chat?
Yes, it should be up on YouTube. Yeah, it should be up on YouTube. Yeah, and then so Edwin's come before. So you know, I learned from experts. So Seth Lloyd, Maria Schuld, so Seth's at MIT, Maria's at Xanadu / Penny Lane, or Bob Kuka. I've been watching a lot of his. He's done a lot with natural language processing and quantum. So he's at Quantinuum, right? So typically every organization has at least one expert, right? So, you know, that's more visible, you know, you can watch their videos and, you know, follow their papers, those types of things. That's a good approach too. But yeah, it'll take a while. For me, it was way harder than I thought, but I also got done way more than I thought by this point, because I was counting on Q3 to just get like a binary classification. Now I did a bunch of them, and then prototyping algorithms, you know, within that model, comparing things. So, you know, it doesn't hurt to present on literature, like a short little one-page reviews I've done. But now I have a project board, you know, can go through and, you know, I know what the focus is. So moving forward. So yeah, you'll have a lot of things that you're not quite sure what's most efficient, but the worst thing is just to not do anything, right? If you don't do anything, you'll never get there. So it's better it's trial and error. You know, you'll find a route that, you know, you find efficient to take you to a point where, you know, you think it would help with your current application as well. If there's one other thing I can share, it's this YouTube. There's like 4 experts. So Maria, Aram. So there's a algorithm called HHL. So Aram Haro is the H to it. Seth Lloyd is the other L to it. I don't know who the H in the middle is. So anyway, there's if I could find this link, it was a Qiskit, quantum machine learning. And you could find this type of stuff on YouTube. It's just really hit and miss. There's just some stuff that's not human generated. It's just, you know, it wouldn't help you if you've researched a little bit, basically. And I'll find it here. Any other last questions? Here's one. So a lot of you coming from the support vector machine, principal component analysis, clustering, you have to watch this video. That link, that's Seth Lloyd. There's a really good course, quantum machine learning, on edX, and it's also partly on, or scattered on YouTube, I would say. So, but yeah, you just gotta, you know, keep studying it. The future of quantum machine learning, you should really watch this. It might confuse you, like I had to watch it twice, but they're experts, and you have mirror neurons in your head, you know, speaking of medical, and you're basically emulating the things that they say over time. And I would say for that last one, it's fast. It's relatively fast, but you watch it one time, 3 months later, you watch it, really helpful. Awesome. Well, this has been discussion 92, July 20th, for quantum machine learning platforms for healthcare applications. Appreciate everybody coming on. Have a productive rest of the week and have a good night. Take care, everybody. Bye.